Let's look at another periodic system, and that is that of the pendulum. And not as simple as the simple harmonic oscillator, but as long as we keep the amplitude of the pendulum low, we can express both its period and its motion in a very similar way to the simple harmonic oscillator. And we call this the small angle approximation. Okay, so let's take a look at what's going on here. Simple pendulum is another example of a simple oscillating system. Again, as I said, you look at the motion, it's periodic. And as long as our angle is kept small, and you can see this particular pendulum has a fairly small angle, the motion is going to be very predictable. The period is going to depend on the length, acceleration of gravity, it's going to be relatively well behaved. Now, if we push the amplitude too high, the pendulum tends to become somewhat nonlinear, okay? And then the motion actually begins to deviate from the small angle approximation. We see the period actually depends on the amplitude, and also the position is going to depend on the amplitude. Actually, it would depend on it anyway. Okay, so in general, the motion of a pendulum is not a simple harmonic motion. However, for small angles, it doesn't be, saying that it becomes a simple harmonic oscillator isn't completely accurate. But essentially, its motion will become very, very similar. So what we need is angles that are less than about 15 degrees. And in this regime, the period is constant and really pretty much independent of angle. The small angle approximation makes a little substitution. We're going to see that the equations that describe the motion of the pendulum are actually pretty complicated. They also have this sine function in them. And for very, very small angles, we can make an approximation. We can replace sine of theta with just theta, okay? Keep everything in radians. But essentially, if you look at sine theta, for angles that are, again, less than 15 degrees, less than 10 degrees, sine theta approximately equals theta. Now, let's take a look at the actual force on a pendulum, okay? This is Ft, this is the transverse force acting on the bob, which is swinging back and forth. And here it says the transverse force is going to be equal to negative mg times theta. Now, there's no force along the length of the string because tension pulls up and it pulls against whatever force gravity pulls down. In order to get this to obey Hooke's law, we've got to sort of change this. Actually, it goes Ft equals negative mg sine theta, where, again, we can look at Hooke's law. F equals negative kx, and see how similar this equation is to that? Okay, and again, we got here by replacing sine theta, which would be sitting right where theta is, to theta, okay? So instead of having this k constant right here, the constant becomes mg. All right. Looking at the force. Now, if the pendulum is sitting at equilibrium, the bob is sitting at equilibrium, tension pulls up, gravity pulls down, they cancel each other out. But if we offset it at some angle theta, the tension is still pulling along the rope. We can see that right here, okay? But now it doesn't completely cancel out the weight. In fact, the tension only takes care of one component of the weight, and that is the component along the length of the string. So we actually end up with this additional component, and that's what we saw originally. That's the tangential force, or the transverse force. So the tangential force on the pendulum bob becomes equal to negative mg sine theta. And again, we're going to replace the sine theta for those small angles with theta. All right. Okay. One way of looking at this problem is a circular motion problem. And we always talk about the bob following the circular path. And instead of force, let's talk about torque. The torque for a tangential force is equal to the lever arm, which becomes the length of the rope, times the tangential force, which now becomes LFT. Okay, now it's going to get a little deep into the mathematics. And I'm going to jump into a little bit of calculus here and differential equations. So the end result is important. I go through this result because if you are taking an upper level calculus course, here's a nice application that you can use. Okay, so here is the torque on the pendulum bob with respect to the point at which the rope is connected and is stationary. Okay? Now, I know, according to Newton's second law, torque is equal, normally with Newton's second law, is equal to force, force equals mass times acceleration. Here, torque can be written as the moment of inertia times alpha, which is the angular acceleration. So I make that substitution, I alpha, and now I'm going to replace alpha with the second derivative of the angle with respect to time. The first derivative of the angle with respect to time is omega, that's your angular frequency. The second derivative with respect to time is obviously alpha, because alpha is d omega dt, all right? And now I can see I have my differential equation. For a mass, some distance L, the moment of inertia is mL squared. So I'm going to plug that in, make a little replacement right there. Our equation looks like this. I can cancel out m with m. I can get rid of one of the L's, divide both sides by L squared. So this cancels out and this cancels out. And again, unless you've taken differential equations, this is going to mean very much to you. But if you've taken a calculus course where you've looked at differential equations, you would recognize this as a second order differential equation. Second order because it is a second derivative, okay? But it's not linear because instead of having theta here, we have sine theta, okay? All right, so let's do the small angle approximation. Let's say, because this differential equation is really, really hard to solve. Let's say, instead of having our sine theta, we're going to say, we're just going to replace that with theta, and that's going to make the equation linear. Okay? So now my equation, here's the nonlinear equation with that sine theta. Here is now the linear equation. Okay? We solve for that, and it has a solution of theta equals the amplitude times cosine omega t. So looking at this, the angular velocity, okay, or the angular frequency, so it should really be, is going to be equal to the square root of g over L we know that frequency is 2 pi times omega. So the frequency is going to be equal to 2 pi square root g over L. Okay? So that is not the solution to the pendulum. It's a solution to the pendulum when we take the small angle approximation. Okay? So from this, for a simple pendulum, when theta is small, less than 15 degrees, the period of the pendulum, period is inversely proportional to frequency, is equal to 2 pi square root L over G. Oops, I made a mistake there. When I wrote this, frequency is equal to 1 over 2 pi omega. Should have written that. So when we take the inverse, that puts the 2 pi right here. Again, this is for a small angle approximation. Now, for our course, this is the only result that we really need to know. This right here, and of course, the frequency, that's showing the angular frequency, the frequency, which is equal to 1 over 2 pi square root g over L. Okay? Now, what would happen if I would actually have taken this equation right here and come up with a solution to it? Yeah, this would have been a really, really tough one to do. In fact, the solution doesn't have an exact form. There's different methods that we can actually use. We still would get the original result that we got for the small angle approximation, okay? The period would be 2 pi square root L over G times 1. However, as the angles get larger, these next terms become significant and can't be ignored. So this term right here we see is 1/4 sine squared theta over 2, okay? Now, normally, the small angle approximation works because this is small when theta is small. But as the angle gets larger and larger, this term can no longer be ignored. Get to an even larger angle, and these other terms also start becoming significant. Okay? So for small oscillations, where the period is small, we can use the period is equal to 2 pi square root L over G. Okay? That's fine. If the amplitude gets too large, then we have to use some of these other terms, which, again, when theta is small, they're pretty much close to 0. So once again, to summarize, here is our simple harmonic oscillator going back and forth. We know that when we trace it out, it follows sort of like this harmonic sign, like the sine or the cosine. And we look at the pendulum, you know, it's pretty much doing the same thing. Okay? It's really the angle which goes by some harmonic function. Both are periodic. The simple harmonic oscillators, period is equal to 2 pi, the square root of the mass of the spring constant. The pendulum, as long as the angle is small, is 2 pi L over G.